Students, today we will discuss the differentiability of functions of two variables. Suppose fxy is a function of two variables and is equal to sin x plus cos y, and this function is differentiable at every point of its domain, that is R square. Here we have fxy is equal to sin x plus cos y, and if we differentiate f partially with respect to x, we get fx is equal to cos x and fy is equal to minus sin y. fxy is equal to sin x plus cos y. If we differentiate x partially with respect to x, then we take y as a constant and we differentiate f, we get partial derivative of f with respect to x is equal to cos x, and partial derivative of f with respect to y is equal to minus sin y. Now, fx plus h y plus k minus fxy minus h partial derivative of f with respect to at xy minus k partial derivative of f with respect to y xy will be equal to sin x plus h cos y plus k minus sin x cos y h cos x plus k sin y. By putting the value of partial derivative of f with respect to x and partial derivative of f with respect to y, we can write it as taking common h from the term sin x plus h minus cos x. We have h into sin x plus h minus sin x upon h minus cos x plus k into cos y plus k minus cos y upon k plus sin y. We have taken h common from the term sin x plus h minus sin x and minus h cos x. Similarly, by taking k common from cos y plus k minus cos y plus k sin y. Suppose this is equal to epsilon 1 and this is equal to epsilon 2, then fx plus hy plus k minus fxy minus fx at xy minus k into partial derivative of f with respect to y is equal to h epsilon 1 plus k epsilon 2, where epsilon 1 is equal to sin x plus h minus sin x upon h minus cos x, and epsilon 2 is equal to cos y plus k minus cos y upon k plus sin y. Now, by taking limit as h and k approach to 0 individually, limit of epsilon 1 will be equal to limit as h approach to 0 and k approach to 0, because in epsilon 1 there is no term containing k. Therefore, limit of epsilon 1 as h k approach to 0 becomes equal to limit as h approach to 0 sin x plus h minus sin x upon h minus cos x, by applying trigonometric formula CD formula sin x sin c minus sin d, we get 2 cos x plus h by 2 sin h by 2 upon h minus cos x. Limit as h approach to 0. This will be equal to limit h approach to 0 cos x plus h upon 2 into sin h upon 2 upon h by 2 minus cos x. By applying limit as h approach to 0, this will be equal to cos x as h becomes 0, and this limit of sin h by 2 upon h by 2 will be equal to 1. Limit of this expression will be equal to cos x minus cos x is equal to 0. that is epsilon 1 approach to 0 as h and k approach to 0 independently. Now the limit of epsilon 2 as h approach to and k approach to 0, this will be equal to limit as k approach to 0, because epsilon 2 do not involve any term containing h. This will be equal to limit as k approach to 0 cos y plus k minus cos y upon k plus sin y, because epsilon 2 is equal to this one. This can be written as by applying CD formula, cos c minus cos d, this will be equal to minus 2 sin y plus k by 2 sin k by 2 upon k plus sin y, limit as k approach to 0 is equal to minus limit of the function as k approach to 0 sin y plus k by 2 sin k by 2 upon k by 2 plus sin y. By applying limit as k approach to 0, this will be equal to minus sin y plus sin y is equal to 0. This means epsilon 2 approach to 0 as h and k approach to 0 independently. Both epsilon 1 and epsilon 2 tends to 0 as h and k tends to 0 independently. This means f is differentiable at every point in its domain. Now we take if another function f x y is equal to cos x plus y, and we have to show that this function is differentiable at pi by 4 pi by 4. We have function f x y is equal to cos x plus y, then partial derivative of f with respect to x will be equal to minus sin x plus y, and f y partial derivative of f with respect to y will be equal to minus sin x plus y. Now at pi by 4 f pi by 4 plus h k pi by 4 plus k minus f pi by 4 minus h partial derivative of f with respect to x at pi by 4 minus k into partial derivative of f with respect to y at pi by 4 will be equal to, by putting all these values of partial derivatives, this will becomes equal to cos pi by 4 plus h plus pi by 4 plus k minus cos pi by 4 plus pi by 4 plus h sin pi by 4 plus pi by 4 plus k sin pi by 4 plus pi by 4. This will be equal to cos pi by 4 plus pi by 4, it will be equal to pi by 2 plus h plus k minus cos pi by 2 plus h sin pi by 2 plus k sin pi by 2, because cos pi by 2 is equal to 0 and sin pi by 2 is equal to 1. This will be equal to minus sin h plus k minus 0 plus h plus k. By using the trigonometric formulas of sin a plus b, we get minus sin h cos k plus cos h sin k plus h plus k. This will be equal to minus sin h cos k plus minus cos h sin k plus h plus k. By taking h common from minus sin h cos k and this term containing only h, this will be equal to h into 1 minus sin h upon h cos k plus taking common k from the term k and minus cos h sin k, we get k common 1 minus sin k upon k into cos h. This can be written as h into epsilon 1 plus epsilon 2, where epsilon 1 is equal to 1 minus sin h upon h cos k, epsilon 2 is equal to 1 minus sin k upon k cos h. Now when h and k approach to 0 independently, the limit of epsilon 1 will be equal to limit as h k approach to 0 minus 1 minus sin h upon h cos k, limit of this expression, that is epsilon 1 is equal to 1 minus cos 0, because sin h upon h as h approach to 0 becomes equal to 1, and cos k when k approach to 0 will be equal to 0, cos 0 will be equal to 1. This means 1 minus 1 will be equal to 0, epsilon 1 approach to 0 as h and k approach to 0 independently. Now limit of epsilon 2 when h and k approach to 0 will be equal to limit h k approach to 0 of 1 minus sin k upon k cos h. This will be equal to 1 minus 1 into cos 0 is equal to 1 minus 1 equal to 0. Epsilon 2 also approach to 0 as h and k approach to 0. This means epsilon 1 and epsilon 2 approach to 0 as h and k approach to 0 independently. This means function is differentiable at the given point pi by 4 pi by 4. Now see this example. We have fxy is equal to xy upon x square plus y square under root. When xy is not equal to 0 0 0 and value of function at 0 0 is equal to 0, then we have to show that fx is continuous at 0 0 and both partial derivative at 0 0 exist, but f is not differentiable at 0 0. Also we have another function fxy is equal to 2x upon x square plus y 4y square under root when xy is not equal to 0 and the value of function is equal to 0 when xy is equal to 0, and we have to show that this function is continuous at 0 0. Both partial derivative exist at 0 0, but the function is not differentiable at 0 0. By using, as we had discussed in the previous examples, by using the relation, using the formula f a plus h b plus k minus f a b minus h partial derivative of function f at a b minus k into partial derivative of f with respect to y at a b, and expressing this expression in terms of h and k, that is in the form of h into epsilon 1 plus k into epsilon 2, and by taking the limits of epsilon 1 and epsilon 2 as h and k approach to 0 independently. If the limit of the epsilon 1 and epsilon 2 comes out to be 0 0 both, then we say that function is differentiable. Now what is Schwarz theorem and what is the statement of Schwarz theorem? If AB is a point of the domain of function f such that partial derivative of f with respect to x, partial derivative of f with respect to y, and partial derivative of f with respect to x and y, second order partial derivative, all exist in a certain neighborhood of point AB, and f x y is continuous at AB, then f y x exist and f y x at AB will be equal to f x y at AB. From the given conditions, it is clear that there is a certain neighborhood of point A, AB. At every point of this neighborhood, partial derivative of f with respect to x and y and the second order derivative, partial derivative f x y exist. And suppose that a plus h and b plus k be any point of the neighborhood of AB, and we take a function, we consider a function phi x which is equal to f x b plus k minus f x b. Now phi a plus h minus phi a will be equal to, by using this relation we have taken phi x is equal to f x b plus k minus f x b, then phi a plus h minus phi a will be equal to f a plus h b plus k minus f a plus h b minus f a b plus k plus f b. Suppose this is delta square f, say. Then by using Lagrange's theorem, Lagrange's mean value theorem, we have phi a plus h minus phi a will be equal to h phi dash a plus theta h, where theta is a number between 0 and 1, and derivative of phi x, phi x, that is phi dash x, will be equal to f x x b plus k minus f x at x b, and phi dash a plus theta h will be equal to partial derivative of f at a plus theta h b plus k minus partial derivative of f with respect to x at a theta h plus a plus theta h b. From this equation second, phi a plus h minus phi a will be equal to h by using Lagrange mean value theorem and by putting the values of phi dash h, phi dash a plus theta h, we putting in this in equation 2, we get a plus phi a plus h minus phi a will be equal to minus h will be equal to h into f x at a plus theta h b plus k minus f x at a plus theta h b. Suppose this is equation 3. Again, by using Lagrangian mean value theorem, we can write f x at a plus theta h b plus k minus f x at a plus theta h b k will be equal to k f y x a plus theta h b plus theta dash k, where theta and theta dash are the numbers between 0 and 1. From equation 3, phi a plus h minus phi a will be equal to h k f y x at a plus theta h b plus theta dash k is equal to h k f y x a h plus epsilon 1, where epsilon 1 approach to 0 and whenever h and k approach to 0. This means delta square which is given in equation 1, delta square f will be equal to h k into f y x at a b plus epsilon 1. Dividing both sides by h k, delta square f upon h k will be equal to f y x a b plus epsilon 1. Similarly, we can write again the by first equation can be written as delta 2 f upon h k will be equal to f x y at a b plus epsilon 2. Where epsilon 1 and epsilon 2 approach to 0 as h and k approach to 0. Then from the equation 4 and 5th, we get that f y x a b plus epsilon will be equal to f x y at a b plus epsilon 2, and taking limits as h approach to 0, k approach to 0, we get f y x at a b will be equal to f x y at a b. This is Schwarz theorem. Thank you, students. In the next video we will study Young's theorem on partial derivative of functions, two variables. Thank you, students.